has been a tradition of defining them in the following way. Holomorphic at every point. If you have a domain D, then holomorphic at a point Z0, D means differentiable. So it means you have a first order development. And in fact, this coefficient will then be Z derivative of Z0 plus the usual error term. And this is for all Z0 in the domain D. That's it. And the first thing, the good news, is holomorphic in this sense implies it's continuous. And it's continued. That's good news, because that means we can integrate it and so on. In fact, I'd like to make sure you have the right notation here. These are the holomorphic functions, OD, I mentioned this, these are the holomorphic functions. And OD is a subspace of the complex valued continuous function. Complex valued is implicit in this discussion. Complex valued continuous. That's the good news, but a priori the bad news, or interesting news, such functions are not a priori continuously differentiable. So f, such functions, and the homomorphic, they have a derivative, r. And now I write the word a priori here because, in fact, we will prove that they're smooth, much better than smooth, as you know. But a priori, they're no better than differential. F is no better than just differentiable. And I devoted the whole lecture yesterday to proving that they are better. Right. So, the lecture yesterday was on Rousseau regularity. Let me even draw a picture, precise picture, which I implicitly proved yesterday, so I'll go through the details again today, sketch at least. If you have a domain D, and you have a point C0 in D, D is oriented boundary like this, you take any disk around Z0, which is contained like this so D delta of some radius R, just for fun, R about Z0. This is my notation, so in case this is a notation. So the disk of radius R, this is delta here, so the disk of radius R should be contained in D. Maybe relatively compact to make sure it's there's no discussion here. And the statement is, the regularity theorem is, F homomorphic on D implies that its restriction to this disk is a convergent power series. Convergent.
Excuse me?
Yes.
So the notation of the double subset of D, that means
Relatively compact, so.
relatively compact itself means?
Yeah, relatively compact means that its closure is compact. So, the point is, we like to have open sets, but we also like to have them reasonable, so.
Okay.
Thank you for asking. This notational thing is, the word here is relatively compact. And relatively compact means this picture, right? And that means closure is compact. So relatively compact. Thank you for the question. Means closure compact. So these are the good places where you can discuss convergence and so on, compact convergence. And if F is holomorphic on D, I mean, it doesn't necessarily have a power series development on D, because D may be mysterious. And as you know, power series converge in disks. You know this from your basic analysis course, right? Or if you look over the reals, they converge in some interval. They have a radius of convergence, which we'll discuss in a minute. So you might have another point here, Z1, and you might, well, let's even make it close here, Z1, and the disk around Z1, the big disk around Z1, it'll have a power series development here, but the power series development on Z1, well, we'll agree here on this, but you don't have a power series development on Z0 plus Z1. You only have it on disks. So somehow disks are playing a role here. Okay. So that's what we proved yesterday. And let's go through the proof so that, yeah, we can make sure that we have the details in our mind. Yeah, I always like to attach funny words. How do you spell puzzle? L-E or E-L? Huh?
N-E.
L-E. Puzzle. Yeah, that looks better. So I always like to attach funny words to things like this because it helps us remember. Yeah. So Goussat's puzzle that's of relevance is this. You take a rectangle, and we take this is the boundary of the rectangle. This is outside rectangle. R. Sometimes when I'm writing my notes, I even write R outside. Yeah. And you take an inside rectangle here of a point zeta, and you take an inside rectangle here, and now you have the induced orientation, so that means that the domain stays on your left if you run around the boundary, so you have this. And I called that thing yesterday this baby rectangle around zeta, so let's call it R epsilon, and let's even emphasize that it's around zeta. And I said yesterday, for convenience, just for convenience, I can assume that 0 is here. I can make a translation of the whole picture, so I can assume that 0 is here somewhere, so that this whole thing is in a disk about I don't know. Doesn't matter. Some disk around here, the center someplace. I don't want to make the center here, so and then I can assume 0 is here. And the reason we need that business is this, that later on Z will be running around the outside and zeta will stay inside this disk. And so we know that the distance from Z to 0 is bigger than the distance from zeta to 0. In this picture, what we need then is zeta over Z. So zeta is nearer 0 than Z, is less than 1 in absolute value. I want 0 to be there, and it's obvious I'm going to make a power series expansion here somehow. And the only tool of power series expansion is the geometric series. And therefore, I want to have some ratio here that do that. And I explained that yesterday, why we need that. So that's the situation that we have. And then we do the puzzle, and we talked about it yesterday. It's the same as this puzzle with or without zeta. And the puzzle says that f at zeta equals the integral. Now let me write it. I wrote it yesterday with Cauchy kernel, so let me just write it. Integral around the boundary of R of f of z. I emphasize that we're integrating with respect to z. This is just notation of the Cauchy kernel. dz. That's what I did yesterday. Listen. Okay. And now what is the Cauchy kernel? The Cauchy kernel has a big singularity, a good one, at zeta. And that's the reason you pick up f of zeta in this argument. Now, you need to keep in mind something, how this goes. Right? The way it goes is with the puzzle. The puzzle first proved, I gave the proof of Gustave when you have nothing in the middle. And the puzzle proves that the integral around the outside boundary is 0. Okay? But if you put the puzzle in here, it proves that the integral, it's the same exact argument, but it says that the integral around the full boundary, which is the outside boundary minus the inside boundary, is 0. That's the deep argument that if something minus something else is 0, then the something equals the something else. Yes. And then you take the limit as epsilon goes to 0, and you use, well, this is continuous, there's no problem. So for small epsilon, this thing is effectively f of zeta, and then it's a question of what the integral of the Cauchy kernel is, and the integral of the Cauchy kernel is 1. Okay. So I recommend an exercise that if I were you, I would pose the following exercise for myself. You understand, I am sick and tired of professors posing exercises for students. It is stupid. It has nothing to do with life, right? If you go to work for somebody at Google or someplace, you work in a team and you're posing, the team internally poses exercises. The boss doesn't even care what you're doing. He or she cares that you're serious. Yeah. And you're thinking about deep, interesting things. So the exercise here, you need to practice posing exercise. The exercise here is check the limiting process in the puzzle. And now I will come to Avik's remark. Last time I was hoping to get this nested sequence. It doesn't matter. You just have to have a sequence, convergent sequence of rectangles. And they don't necessarily need to be nested. That's very important because you don't get the right estimate otherwise. Okay? And so you could ask a question here, what does it mean does it mean that, for example, in this concrete situation, a sequence of rectangles converges to somehow a trivial rectangle? Okay. What does it mean that a sequence of rectangles converges to a trivial rectangle? Okay. And then if you're thinking a little bit better question, you see this is very nice. You sit here and you ask yourself questions. Suppose Kn is a sequence of sets, and then you think for a while and you realize that you better have compact sets, sequence of compact sets. In a topological space. X, and then you ask the question, what does it mean that Kn converges to some other compact set? What does it mean that a sequence of, here's a sequence of compact sets, or compact rectangles, here's a compact set. You thought about this trivial, seemingly trivial case of rectangles jumping around converging. Yeah? You somehow figured out what that meant that they converged, right? And then you ask yourself, obviously, look, I better understand the general situation. The general situation is, let X be a topological space, any one you want, maybe you impose metric or something, I don't care. And see what, if I can get a good definition of what does it mean that a compact set converges to another compact set. This is an obvious question. If you can't ask these kind of questions in life, you can't do mathematics and you can't really do anything serious in life. Right? You start with no, I'm dead serious. You start with something you think you know. I screwed it up yesterday because I said nested sequence. Yeah, Abik pointed out, he's in the team, he points out you don't have a nested sequence. And I say, okay, I fix it. I just fix it like this. Okay, it's good, it works. Let's check out what that means. I went blah blah yesterday. I said you take a convergent sequence of rectangles. I know what that means. Maybe you don't. Yeah. Figure out what it means, check it. And in the end, you're making the obvious jump from something almost trivial to something serious. And you're just following your note. This English expression, follow your note. Maybe in your mother languages you have the same. You're following your note. Yes? I highly recommend that. Okay? Well, and by the way, the first person who asked this question and answered it is very well known. This is called the Hausdorff topology on compact set. Yeah. This was a great scholar, a great intellectual, and he thought deeply about everything, including philosophy and literature and so on. He was in Bonn, by the way, as a professor, and of course, as a Jew, was distinguished again, well, not distinguished, was discriminated against, and eventually he took his life. But when I'm in Bonn, I walk around on the street. It's called Hausdorffstrasse. It's very nice, and I think of the Hausdorff topology. But he would say it's trivial, but he thought of it. Okay. Okay, I think that's the kind of thing I mean by these questions, and that produces this wonderful result. That produces this wonderful result. Okay. And this produces the Cauchy-Indigo formula. No, I call it, I'm tired of writing it usually, so I call it the Cauchy-Indigo formula. Cauchy integral formula, which says that the Cauchy kernel is the right thing to look at. It says that the integral of f of z around the boundary of this rectangle, so f of zeta, this is, my friends tell me my zeta is bad, that's a zeta. Around the boundary of that rectangle is the integral f of z. Well, let's write it with 2 pi I here. And let's emphasize the z's in the boundary. Okay. And as I said, I'm going to assume, for example, that 0 is in there. So this says that this is equal to, let's do it here very slowly. So you should say your professor is sometimes very impatient and doesn't have the patience to calculate these things out. So you should get mad at him, but very lacking him, so you should do it slowly here. So we divide by z, z's outside, and so z is never equal to zeta, so you can divide by z. This thing is never 0 here, so we divide by it. So we write this thing here. There's only one thing in life that you can use, is the geometric series. So when you're trying to prove convergence, the first thing you try is to try to find someplace in geometric series. Okay. And now the geometric series converges here because the absolute value of this thing, the way I've set it up, is less than 1. Okay. And so this thing converges, and so we can write this here in some way as, let's write it really slowly. Integral, I'm getting tired of around the boundary of R boundary of R. F of z over z sum z over zeta. Easy. Okay. And now in mathematics you have a sum inside the integral, and you would like to say that's a sum of those integrals, right? And now you have only one, at first in elementary mathematics you have precisely one technique to use in elementary mathematics for taking this out. And we have a question here, is question, do we really understand what we want to prove here? I understand, because I've done a lot of analysis in my life. I understand when I say an integral. And what I want to understand is I want to put this thing outside. So what I'd like to do is something like this. This is, let's put the sum out in front. That's what somebody said it. Put the sum out in front. Geometric series of development is this. Well, I forgot the n, so maybe that's what you were saying. And now I'm tired of that n, so I will erase this n. I know this is bad for your paper, but I will put this here. Yeah. And now I have the sum of the zeta n's, and so that's the power series and the coefficients of those things. So what I want to do, this is sum n equals 0 to infinity of now the coefficients are the integrals f of dn n plus 1 dz of zeta to the n. Yeah. And of question is, do you really understand what we want to prove here? Okay. Do you really understand what you want to prove here? Well, what you want to prove is that you can take the sum outside. This is the sum inside. This has nothing to do with the sum. You maybe hear blah blah, can you exchange the sum and integration? You hear that blah blah by some mathematician. That's not the right blah blah. The right blah blah is when is the limit of an integral the same thing as the integral of the limit. When is the limit of the integral the same thing as the integral of the limit? That even has a nice ring. It has nothing to do with the sum. You apply it to partial sums here. Yes. Fn is the partial sum in this case. Maybe why shouldn't I write F? Well, okay, I'll write where are the partial sums here? These things here. Sum. Let's write m here, and this is the limit over m. So the partial sum, and in this case, Fm is the partial sum of these integrals. I know you people, you're great students, and I like you very much, and so on, but sometimes you forget to write down slowly what you're trying to prove. And what you're trying to prove is this. Okay? And then, if you have a hard problem, you're working for some company, or you're working as a professor, or you're trying to prove some result, you want a publication maybe. And, well, she had a nice internship at somewhere, she maybe has a publication. That would be nice, Crystal. Yeah? And someplace you want to prove, you need this. Yeah? Someplace you need this. And you say, oh, I need it. Now, nowadays you can find out a lot of information on the web. Right? You can find out a lot on the web if you hack around a lot on the web, and that's just fine. I have nothing against it. So, when is this? That is a highly non-trivial, you realize this is a highly non-trivial question. This is the fundamental question somehow of the subject in real analysis. So you ask, what is the cheap theorem here? Because you were beginners. What is the cheap theorem here? In other words, what is a mega condition on this convergence where you can be sure that you have no problem? Okay. And I told you guys in analysis 1 the cheapest theorem, and the cheapest theorem is uniform convergence, yeah, of continuous functions. The cheapest theorem is uniform convergence of continuous functions. So the very easy cheap theorem is uniform convergence of on compact subsets. Of continuous functions. And what we're dealing with here, of course, is a power series, and of course, it's trivially uniform convergent. Why? Because you have the estimate with the geometric series, right? It's trivially uniformly Cauchy, right? Because you have the estimate with the geometric series, right? So, a professional mathematician, when he or she is discussing this matter, never bothers to say much in this simple-minded situation because it's so obvious stuff. Okay. Now, just let me give you a preview. Once you're asked that question, when is that the case of cheap theorem? What about what happens in general? my mind, what you need to do at your stage of the game is ask a mathematician. Yes. And the subject here that handles this, first of all, is basic real analysis. Okay, and if you're at a university, when you're a graduate student, for example, you find out who's teaching courses in basic real analysis, and you ask this person, what's sort of the state-of-the-art theory here? Okay, and he or she will tell you, well, what you want to do is he will mention this guy's name, and this guy, French guy. He invented a lot of stuff, actually was well known to the Italians. He invented a lot of things that handled this situation. And some of his colleagues were of great importance in this subject. And so on. And these professional mathematicians go to say, well, you just consider the Lebesgue-dominated convergence theorem. That's a standard theorem. Or you consider Fatou lemma. You consider all these various things. And it'll blow your mind, you're tired, and you go home and you drink a glass of wine and go to bed. But at least you have some view of that there's some theorems of this type. Theorem of Dini, there's an Italian, but the monotone convergence theorem. So if there is any kind of special convergence going on here, it works. Okay, but the entire theory of measure theory was developed with these kind of questions in mind. And the second year students are taking Kavan's course, I think, in probability theory or, yeah. And you see, when you have big data, it's a fancy word, big data, right? Then you have what are called random variables, which depend on n, and the explicit values of the explicit nature of these low n, these random variables is not interesting. It's big N. And questions of convergence, what's happening for big N is important, and is what we do in the theory of probability. And the first theorem you will hear about from Kavan is called the central limit theorem. So it says if you scale these variables correctly under mild assumptions, these things converge to the Gaussian distribution. That's fantastic. And the Gaussian distribution is therefore behind almost everything. So you really want to know what it means, how these functions, these are functions, how these functions are really converging. What is the right notion of convergence? And whether integrals, after all, an integral is an expected value. Any physicist knows that. An integral is an expected value. An expectation, it's not called expected value, expectation is right in quantum. You want to know what you're doing, and so you want to know what kind of convergence is necessary, and you see what happens in this discussion. You start, look at this blackboard. You start exercise, check the limiting process in the puzzle. What's going on? Hausdorff topology. Ah, very interesting. What in the devil do we need to prove this thing? Well, we need almost nothing. It's a joke. We need the uniform convergence geometric series. But what do we really need in general? What's going on? You see what I mean? And you end up in good, serious, modern mathematics. Right. One reason you want to be at a university, for example, as a graduate student, also particularly physics people, get to know mathematicians. Yeah, get to know which mathematician to talk to about things like this if you need some. Right? That's the only way. I guarantee you, it's the only way. Plus the web. Yeah. No, you have to be careful, but the web is extremely useful. You have to be careful. Deepak looks around on the web, can't find anything, and so on. And I forced him yesterday to make a calculation. Maybe he actually did it. So, Yeah, right? Maybe that's the thing to do, like, you hack around on the web, you can't find anything, you hack around some book, you can't find anything. You say, oh, I have to make a calculation. Yeah. And then you maybe prove the thing you try to prove. Yeah. Okay. That's what I have in mind about good questions. Okay. So we proved this yesterday, the power series expansion yesterday. So Boursin implies smooth, much better than smooth, actually, they're always right, much better. Which implies, this is the kind of thing you should keep in your head. You can use green. In dimension 2, or more generally Stokes. And which in my formulation is integral around the boundary of anything over one form is the integral around the thing of d to the one form. And many of you have understood the first part of this from Caven's course last year, some of you. And some of you are taking Caven's course, not Caven, Sirden's course this year. I talked to Sirden last night. He's certainly going to prove this theorem in some way. Okay. And I believe you should try to really understand Stokes theory. So I believe two basic theorems. Stokes. Yeah. And the theorem on constant rank. Stokes' theorem, we've talked about. Theorem on constant rank means that it is, I'll make a provocation, so you should check it to make sure you understand. It's a question, answers a question about linearization. Now that statement there is a professional statement, so you should ask, what the heck does that mean? Okay. And here's what it means. Okay. Here's what it means. You have a map. My notation means when I write a pair here, I mean that f of 0 equals 0. I localize the map as 0. Okay. Let's say this is a smooth map. Okay. The question is, can you linearize this map? You get it? Can you linearize this map? So, I've been pointed out that the second year students have had a disadvantage of not having much linear algebra yet. Okay. But you do have a little linear algebra, I think. Right? So you know what a matrix is. Right? You know what a matrix is. That it means, can you change variables so that this thing's a stupid matrix? You understand what I'm saying? So the question is, does there exist, I'll let you decide where the diffeomorphisms are. So does exist question P and C, so that this map, should be diffeomorphisms. So that this map is linear. So this map is a matrix. You get the question? Isn't that a reasonable question? I see two people in physics only. You destroyed all physics students. You have to point to that. It's good. Okay. Almost everything you do in physics is done by linearizing. Right? We linearizing at this, we linearize at that, we linearize at that. When can you linearize? Well, that is the answer of the theorem on constant variance. And it is a big question in mathematics. If you have a map, let's say a fixed point, so n equal m, and that this thing is a self-map. When you have a map, when can you linearize it? You'll be excited to hear it has to do with the nature of the eigenvalues of the differential. This is such a hard problem that Poincaré, you heard the name Poincaré, I think. Poincaré figured out how to linearize with the power series method in a certain context. But he didn't care that the power series was not convergent. So he introduced a non-convergent linearization, which was useful, however. Very interesting. Almost physical. You have to understand Poincaré is essentially a physicist. So he had big fights with the people like Felix Klein, who was a mathematician. Poincaré was very, very physical in his thinking. But very interesting ideas about linearization. One of the nicest articles on the subject, which maybe some people find as elementary, but I don't, is an article of Shlomo Sternberg and his thesis at Princeton. I think Princeton. So, Shlomo Sternberg, a mathematical physicist, and he knows very well the question about linearization. These are the two theorems in analysis. Stokes' theorem and the question of how do you deal with linearization problems. And the first theorem on linearization problem is the theorem on constant rank. Well, we may now, back to complex analysis. So if f is holomorphic, maybe I'll be a little bit less sloppy here. I'll put the closure here. That means holomorphic in a neighborhood of a domain D with reasonable boundary. Then Stokes or Green's or whatever you want. Integral of f of z around the boundary. dz z. That's Stokes' theorem. That's all there is to it. So, and basically, in several lectures, I proved almost nothing. I just applied Stokes' theorem. Pointed out that you can apply Stokes' theorem because we have Guizot's regularity, and I apply Stokes' theorem and I get this. You see this is called the Cauchy integral formula. We get the formula, and this is called the Cauchy integral theorem. Okay?
So the reason we say it's the condition for applying Stokes' theorem is that it's continuously differentiable,
That's right.
and therefore, like we saw, we say at every point we can find such a converging power series.
Right. So it's far better than continuously differentiable.
Okay. Yeah.
Okay. Okay. So, in some sense, as you see, I go around all over the place in my lectures, purposely. But the essence of this is you're allowed to apply. You get a regularity theorem, so you're allowed to apply Stokes. And you're fin. And that's basically what you have. You have the Cauchy integral formula. You have Cauchy integral theorem. So let us make some remarks on convergence. I made some. Okay. And if you're thinking, well, you will make, the first remark you will make is this. The holomorphic functions on D are contained in the continuous functions on D. Don't be afraid to write something trivial. That's important, right? Then you observe that you can add continuous functions. I'm being a little bit, I mean, you know, at nighttime when you're very tired, you should make trivial remarks, and sometimes they're not so trivial. So you can take linear combinations of two continuous, AF plus BG, where A and B are constants, right? That means that thing's a vector space, right? Vector spaces mean you can do that, right? But the big time thing is if F and G are continuous functions, then so is F times G, right? Right? So you see, people take a beginning course in algebra, and they talk about the notion of a ring and the notion of a C algebra. And the first question is, when you go blah, 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 what is a ring in a C algebra? I ask you, what is your favorite ring? What is your favorite C algebra? Well, this thing is a C algebra because it's a complex vector space where you have multiplication that works beautifully and is commutative and so on. So this is a C algebra inclusion. There's a little bit of, you ask yourself, is there any meat in that statement? There's almost no meat in that statement. But the little bit of meat is the product of two holomorphic functions is holomorphic. Right? And to check that, you say, well, I can check it. It means this. The Leibniz rule for the D-bar operator is obvious. And since the Leibniz rule, I never know, is it TZ? Okay, Nico, you're German. Is it TZ or just a Z for this Leibniz?
Not totally sure. I think just Z.
Just a Z. I
It
get really
looks weird
confused.
though.
It's a question of spelling and use spelling, but I make a mistake because they're cookies by the name of Leibniz cookies. So Leibniz, that's Leibniz. Leibniz rule, and that proves the product. So this is an inclusion of C algebras. You have two C algebras. You have the continuous functions and a beautiful subalgebra. And then, because you all, particularly because the secular students here have my real analysis course. But everybody knows that what the topology is on the continuous function. Right? It's uniform convergence on compact subsets. So, uniform convergence, this is on compact subsets. This means for all K contained as a compact subset in D, right? The suit norm F n, I'm talking about convergence of sequence, over K goes to 0. Right, that's uniform convergence on compact, right? Subsets. Now, if you have a good analysis course, the emphasis should be as follows. It says, given K and given epsilon, there exists big N, so that if little n is bigger than big N, this thing, sup norm over K, is less, yes. But the question is, what does that big N depend on? It's very important. Big N depends on epsilon, obviously, and K. So for big K, you need bigger N. You believe me? If you don't believe me, look at this sequence over the reals. Fn of x equals x to the, I don't know, something like 1 over x to the n. No, that's no good. I don't know. Something. Yeah. Maybe this is good. On the unit interval, say 0 to 1. Right? That sequence converges to 0. However, at the end point, it's identically 1. Right? So this big N that you're going to have, I mean, these functions, as you know, these functions look like this. Here's one. These functions look like this, and look like this, and look like this. You see what I'm saying? Right? And that says the big N you need depends on the epsilon. Same thing here. Okay? So, this is the standard topology on the continuous functions on D. And the key fact is this thing is a complete metric space. Okay? That means every Cauchy sequence, a sequence converges if and only if it is Cauchy. If and only if it's Cauchy in the metric. And you should, then the professor says it's a metric space, and you say, what is the metric? Question, what is a good metric? It's true that it's a metric space, but the professor gets a little bit tired of talking about all this stuff, so he or she's just not willing to answer that question. You have to figure out what's a good metric. This space, the French, by the way, this is French mathematics here, the French realized that you need to talk about topological vector spaces and think about what are the good metrics and the good conditions and so on. And the important statement is that this space is a Frechet space. Frechet. French mathematician. So, yes, you get very tired if you read Bourbaki, but you can find elementary places to read about these kind of topological vector spaces. Okay. These in the many notation topological vector spaces. Okay. Now, question. This has a standard topology. It has many nice properties, and we just discussed them. Yes.
So how does uniform convergence on compact subsets actually define the topology? I mean, topology is what defines an open set.
Right.
So how do we define open?
Okay, so fine. So the magical word here that you're going to learn about is this. So this is there is a metric on this space which we'll learn about.
Yeah, right.
That gives uniform convergence on compact subsets. So that answers the question first of all. And the second answer, which is a better answer, is that the topology is defined by semi-norms. And the semi-norms are this. You have, well, for example, you have, here's something you might think is a norm on this page. Namely, you take a compact subset, and you take the norm over that compact subset. Right? So you say something like the topology, the distance, you would say the distance between F and G is the semi-norm. So take the suit norm of the difference on a compact subset, right? But that is certainly not a norm, because it's possible that G and F are equal on K. Yeah? And so you say that's bad because it's not quite a norm. Okay, but then you do it, so you say this, okay, there you go, you're looking for your open neighborhood. Right? It says the suit norm over K it should be, I'm talking about an open neighborhood of, say, F. Is a set of G's so that the suit norm is small. Well, it's not really. Okay. So you say, well, you know what? What I'm willing to do here, this is going to generate a topology. What I'm willing to do is do a bunch of these. And let's look some finite set of i's, of course not an infinite set probably. So a bunch of inequalities, right, define that. And that defines the topology. The open sets are defined by these semi-norms. And then when you have a semi-norm space here with countable topology, you can, in this almost standard way, build a metric that does it. Okay? As you might guess, it's just the sum of the semi-norms as some compact sets cover the manifold, that cover the space. The trouble is that that thing doesn't converge, so you have to scale it and make it converge. Okay, so you can find these things easily on the web. So I'm close to the, I'm finished with the, no, I have time, right? I have 15 more minutes, very good. So, I think it's very interesting. And thanks to Nico for his nice questions. We have semi-norms on the continuous functions. You have the semi-norm, restricted semi-norms on the compact for the holomorphic functions. This is okay. This is subalgebra, couldn't be better. This is metric space, couldn't be better. This thing is complete, couldn't be better. Okay. What is the right question to ask here? Well, first of all, get this thing straight like Nico's getting. We got it straight. Well, what is the right question here? The question is, what is the right question? No, really, well, you have to agree. I have continuous functions. I have inside the continuous functions the holomorphic function. Right? It's a subvector space. Then you say, well, I know the picture. Here is R2, and here's a subvector space. W is a subvector space of R2. It's a line, right? By the way, that's the first question. Draw a picture. Can you draw a picture of subvector space? Okay. There is Rn, and then here's Rn, and here's a subvector space of Rn. Maybe the dimension of this thing is equal to n. Right? That's how it looks. I hope you had that feeling. From Foundations of Mickey Mouse Linear Algebra 1 and 2. Right. Okay. What you say? Okay. Here is the continuous functions, space of continuous functions, and here is the space of holomorphic functions. It's a subvector space, right? What is a good question here? Is that picture right? What's dangerous about this picture? You guys, I mean, what's wrong with that picture? What could be wrong with that picture?
You don't know the dimension of the continuous function.
Hmm?
You don't know the dimension of the...
Well, it's infinite. Well, no, that's the first good question, I think. But I think the continuous functions, that's a good question. So what I would do is I take the function 1, I take the function x, I take all these functions here. In my mind, they're independent. So you just check they're independent, so the dimension is infinite. That's already the key point. In finite dimensions, everything's cool. But in infinite dimensions, what could happen? You have a subspace of an infinite dimensional vector space. It could be dense.
Could be what?
D-E-N-S-E, dense.
Oh.
I'm saying that this picture could be wrong. Okay? Okay? Let's think about this situation. You should think about this situation. Let's think about something that you probably learned about in Mickey Mouse Analysis 1 or 2. A function has a Fourier series, or if you're lucky. Yeah? Right? A function has a Fourier series if you're lucky. The physicists do it all the time. Write down a Fourier series. Quantum mechanics, that's all you do. You write down they're waves. And you add up independent waves, and this is important, right? So you have a Fourier series. Let's look at this thing. F equals sum a n. Well, let's make it complex. E to the I n x. I don't know if you did it that way. Did you do it that way, or did you do it with sine and cosine? That's okay, right? Fourier series comes on a circle, right? Right. You look, every function has a Fourier series. In some sense, that's maybe not equal, but it's equal for a lot of functions that are good. Right? Right? That says that these guys, the span of these guys, A-N, E-I-N, all of these things together gives you almost every function, but it doesn't, yeah? Suppose, what is the converter? Maybe it only approximates, right? Maybe it only approximates, right? Or, what about these guys? We talked with Eglise about, what about these guys? And this is simple, because I knew you had some Fourier series, I mentioned that. But what about these guys? Right? You certainly learn that every continuous function can be approximated by a polynomial, right? That's a fundamental thing. That's Weierstrass proved that fact. But if you look at the space of polynomials, that's a subalgebra. It is certainly dense because every continuous function can be approximated by a polynomial. But it's certainly not the whole thing because not every continuous function is a polynomial. Same thing with Fourier series. So the amazing intuition is that if you have A contained in B, and B is something like that, and both are linear spaces, it's possible that it looks like that. The finite dimensional picture is wrong. Okay? You got it? You see what I'm saying? A can be dense in B. Dense means everything in B. The irrational numbers are approximated by the rational numbers. I mean, right? That's not the same thing. Well, maybe it's the same thing almost. Right? I'm talking about linear subspaces. Okay. So now, after I've gone blah blah about this, what's the right question here? What's the right question?
Is it closed?
Is it closed? Isn't that the right question?
So it's kind of the opposite to ask whether it's dense.
Oh yeah, okay, if you ask both things, is it dense? Yeah.
When if it's closed, can
Okay, you can ask both questions. What's the closure of it? No, it's a reasonable thing. What do you get? Yeah. What's the closure of it? And Prabhupada asked, maybe, I mean, I think he knows actually because he's thought about these things. But I mean, if you haven't thought about this thing, that's a reasonable question, right? Is it closed? Right? Is it closed? Okay. That is a good question. Don't you think? You asked a question, Prabhupada. You like the question, right? He's smiling like crazy, so he really likes the question. Okay. So, then, after you've asked that question, which I find a really good question, then you say, okay, and then we put Nico's question together with it. It's a stupid formulation. Suppose Fn is holomorphic, and Fn converges to F, which is, I don't know what the heck it is, continuous, right? I'm taking a point on this boundary, and I want to prove, so I'm answering both questions. I want to prove that it's holomorphic. That's the question. All right? I think that sequence of discussions is very important. Right? Okay. Watch. Check the argument. Integral Fn over z minus zeta, Cauchy kernel, dz. That's Fn. I'm being sloppy here. On a disk. Yes? Converges to integral f of z dz, and this converges to f of z, this converges to f. Right? Fn converges to f. Therefore, the Cauchy formula, Fn converges to f in the Cauchy formula. F is continuous, I don't care, it's okay. Fn converges to add. This says that this thing is equal to add. Cauchy integral is equal to add. And now check that as a function of zeta, the Cauchy integral is holomorphic. Right? Check that it's holomorphic. That's the key thing. The Cauchy integral, no matter what f is holomorphic in zeta. Because you just take the derivative with respect to zeta bar and it's 0. So I suggest, as a sequence of questions, go through this argument and make a nice proof at the end. And it's worth something. I see Abek thinking, and you think, I like it because I see you thinking. You're okay with it?
Yeah.
So it's a key. The Cauchy, you can represent the thing as an integral formula, and this integral, no matter what f is holomorphic in zeta. As long as you can integrate that, I mean, it needs to be continuous. Okay? Yeah.
And is the whole thing then defined as Fn, or is it some other function which we find to be that whole expression? Because we say Fn equals something which depends on Fn.
Okay, let's go through oh yeah, I have a minute or two, I don't want. Okay. If Fn is holomorphic, Fn can be represented by the Cauchy integral formula on a disk. And this is enough to discuss this on the disk. So Fn is this. That's the first thing. That's equal. Okay.
So Fn of zeta that equals that.
If you like, yes. Let's put zeta here. I'm sorry. Yeah. Put Fn to zeta. Okay, that thing converges uniformly to f of zeta, if you like. Okay? Which is a continuous function. Okay. Right. That's all we know. Continues uniformly to a continuous function. But this integral converges uniformly to this integral. And this integral is therefore f, because this converges to f. Okay? And the answer here, no matter what you put in here, we put in here J for junk. Right? This, if you put J for junk in here, this thing is holomorphic. It's no longer junk. It's only junk if junk is holomorphic. Yeah? Okay, so this thing is, and it's holomorphic in zeta, so this thing is holomorphic in zeta. And that's the proof. Okay? So Prabhat is happy, it's closed. Yeah? But that's a big deal. It means a sequence converges if and only if it's Cauchy. Right? That's a big deal. Thank you very much. Have a nice week. Thank you, Crystal.